system. And accordingly, we have developed a data loader that provides a unified interface to this otherwise disparate dataset and map formats. So this data tool is called Trash Data. So besides making our life easier, this can also enable some new research directions, such as generalizable prediction models that can rapidly adapt to new domains. And the Trash Data has also significantly accelerated our research development process. Virtually all of the projects we are discussing today leverage it to provide the data in a standardized format and share common utilities across products. For example, map APIs and data transformations and the customizable visualizations. For example, we show an example, visualization example on the right. And of course, finally, such a tool is useful for the broader academia community. And we have received great feedback and the engagement from the community since releasing it publicly last year. And if you are interested, definitely check out this Trash Data tool. And of course, unlike building a single module for autonomous driving, building the entire AV stack is even more challenging, especially with state-of-the-art modules that are integrated and can be trained end-to-end through the stack. So to facilitate the process, we have also been building our differentiable stack with the mindset that it can serve as a full AV stack tool for the broader community. So our differentiable stack tool interfaces with basically three major components. The first one is a public state-of-the-art perception library, MM detection 3D. The second one is our internal state-of-the-art prediction planning libraries, and finally a suite of closed-loop simulators. And of course, we use the Trash Data tool as the intermediate representation or interface. So as such, we can easily switch from one algorithm to the other in our AV stack, as long as these algorithms are developed on top of these libraries or compatible with the Trash Data interface. And these include virtually all of the prediction planning models developed in our group, since they are based on the Trash Data interface. And also, this stack can significantly accelerate the integration process for cross-team collaborations at NVIDIA or with other external researchers. So we are hoping this Trash Data and the differentiable AV stack can lower the bar for full stack AV research. And at the same time, we also hope this diff stack tool can also serve as some entry point to driver sim, which is also developed at NVIDIA for researchers in the future. So to summarize, today I basically talk about three things, three major things. The first one is I show that the modular AV architectures can work with very well if designed carefully. For example, our modular stack achieves new state-of-the-art in the Carla challenge by a large margin. And the second, I talk about how we can make modular stacks differentiable and thus making them scale with the foundation of autonomous vehicles. And this architecture, while still modular, ensures safety and interoperability by certifying each sub-module independently. And the differentiability of each module allows us to train the model end-to-end and seamlessly propagate all the errors, maximizing efficiency and of course performance. And finally, in the big data era, the significance of neural representations can be overstated. And our goal is to learn these representations from data, capitalizing on the emergent properties of self-supervision. So we hope that these learned representations are integral and complementary to our end-to-end architecture. And with that, I would like to thank everyone for listening. And if you have any questions, feel free to contact group members at our group or contact me directly. Thank you so much for listening.
Thanks, Yue, for the wonderful presentation. So let's now have some time for questions. Anyone from the audience? I can start one to kick off the discussion. So,
okay.
For the third part, you talk about this emerging and wonderful new representation. I mean, their representation or their interface from these unsupervised data, and especially leveraging some of the foundation models. So I'm just trying to think, what do you imagine would be the ideal or like really the ultimate representation we're going to use for driving framework? I mean, this kind of whole idea makes sense, right? So we have this differential and end-to-end stack, but I mean, there could be different format of the representation used inside this idea of a differential stack, right? So I mean, either the old representation like you introduced, like these agents for bounding box centric, or this new learned representation, this B view or occupancy. I mean, both kind of can fit into the story, and I can see pros and cons. For example, for this occupancy, I believe it's going to perform very well, especially in terms of semantically, by learning from these large-scale foundation models, because it has seen so much of the concepts, and maybe also geometrically, because it has some learned from some like depth data, like point cloud data. But in terms of the motion behavior, I personally still feel like, for example, I mean, vehicles would be one of the major parts of the driving scenario, right? I mean, other vehicles, right? We still need to learn the motion behavior of other vehicles or road participants in order to drive well. So is this representation good enough, or do you think it's sufficient enough to learn those motion behaviors, or can it be just used as ultimate representation for driving, or like basically what's your thought on that?
Yes, yeah, that's a great question, and thank you so much for proposing this question. And let me answer this question step by step. So for now, I think in the short term, my hope is that these neural representations from foundation models or self-supervised training can first help perception, and we can use this learning procedure as a pre-training algorithm to improve the perception models. So that is a short-term hope. And of course, in the probably long-term hope is that we can use the representation for planning. For example, if we can plan or do some motion prediction on top of this representation, we probably don't need the perception model at all. So we can directly learn such word representation from self-supervision, from a limited amount of data, and then we can do planning and of course control. But like you said, this requires accurate modeling of dynamic objects and static world. I think for static world, this is quite easy, because NERF is good at estimating the geometry, and of course we have the LiDAR supervision as some additional information providers. And also, I think the hard part, like you said, is dynamic objects. So I think the NERF originally has a static word assumption, meaning that we can really deal with dynamic objects. So as a next step, what we are doing now is we trying to model the scene with some 4D fields and to model the scene dynamics. And if we can successfully do that, we basically can learn some per-voxel motion field, and then we can replace or build the prediction module on top of the motion field, or even completely remove the prediction model and doing a planning on top of this representation. And I don't know if if I answer your questions. I guess yes, this seems a very promising next step, and we are actually working on that.
Yeah, I think it definitely answers. Thanks, Yue. Any other questions?
Yeah, thanks, Xinggang.
No.
Okay, so if there's no other questions, I guess we can end here. Thanks again for the speaker, Yue.
Yeah, thank you, Xinshu, and thank you for the organizers.
Okay, sounds good. So, okay, sounds good. Hello, everyone. Welcome back. So now we have our next speaker in line. Is Brady, and Brady is a PhD student at the University of Texas at Austin, working with Philip. His research focuses on practical application of deep learning in the realm of autonomous driving, specifically in the development of effective representation for driving scene. Today, Brady will talk about his recent work on cross-view transformers for perception. And the stage is yours.
Yeah, thanks for the introduction, and happy to be here talking about some work that we had at CVPR 2022 of last year. So these slides are definitely designed for like a broader audience, but if we want to talk technical, feel free to ask questions. So autonomous driving systems can broadly be defined into three main areas: perception, planning, control. And from raw sensor data, perception stack first builds like a representation of the surrounding scene. The planning stack uses this to determine a safe trajectory for the vehicle to take. And then this trajectory is then turned into steering and acceleration by control systems. And in this talk, we'll kind of focus on the first part, on how to build effective representations for driving. So before any planning can be done, we first need to understand the scene around us. For example, we could use some segmentation models and label all the pixels in the scenes that are drivable, or we can represent the scene as maybe boxes and find all the things in the scene that we're not supposed to hit. So these two tasks in particular do provide a lot of valuable information that we can use in driving, but they're not exactly what we need to drive safely. For navigation in particular, it makes a lot more sense for the perception systems to build the representation of the scene in the form of a map. And the map encodes information spatially and tells where the vehicles are, where the road is, the lanes, and is just a really nice compact representation and is directly aligned for downstream planning. And so the next question is, how can we build this representation? And while we humans can do this just by looking around with our two eyes, autonomous vehicles use a variety of different sensors to see the world. So here's what a self-driving car looked like back in 2007. The cars today that you'll see maybe driving around, they look a lot nicer, but under the hood, they're using just about the same sensors. There's GPS, IMU for localization, and then radars, cameras, and arguably the most important part of the sensor suite, the LiDAR sensor. And there's a couple of reasons why LiDAR is such an awesome sensor. It gives you very accurate depth measurements for the scene around you and can actually see just as well as at night as during the day. And the major advantage that LiDAR has is that the measurements really nicely align with the representation we need for driving, which is essentially like a top-down 2D map. But there are some issues. If we take a look at how much these sensors cost, it can get expensive very quickly as the resolution increases. Now this graph is not really updated. It's just kind of pulled from public sites, but this is essentially the trend of how much the LiDAR costs. So if we take a look at how much these sensors cost, we can see it increases very quickly as the resolution increases. And even if price isn't a factor, the best LiDAR sensor today has only 128 channels, which is just slightly above the resolution of the first digital cameras. And to take a closer look at this, if we compare LiDAR scan and camera image side by side, we can really see the differences in resolution, especially for objects further in the scene. So here, you'll see the car, which is just maybe less than 50 meters away. It only has maybe two LiDAR measurements that pick up on it. So this really inspires the question, how can we build scene representations similar to those that we can get from these LiDAR-based systems using only multi-view camera images? To define the task in a bit more detail, we'll use a set of cameras mounted around the vehicle to predict what's going on around us. Specifically, we're given a set of camera views along with calibrated pose and intrinsics, and our goal is to predict a dense map view segmentation of the scene. So previous works build this map by going essentially through monocular depth estimates. For every pixel in the image, they'll predict the depth and project the information from different views along this array into a shared 3D space, and then transform this into a canonical map representation. And these methods work well if the depth estimates are accurate, but they cannot consolidate different estimates from multiple views, nor do they make use of the views partially overlapping. And another important thing to note is that these methods typically operate in less than real time, due to the fact that they're not easily parallelizable. And in this talk, we'll show a way to solve these issues by looking at the task in a slightly different way. Rather than going from 2D to 3D, we'll do the opposite. For any point in the map view, if we knew the height at that point, we could actually directly map back into the camera view. And this kind of simplifies the task quite a bit. To illustrate this in a little bit more detail, for any X, Y point in the map, if we knew how high above the ground this point was, we could easily find where in the image this maps to. And in reality, we don't actually know the height, but for a minute, let's just assume we do. So here on the right is the projected mapping between these 2 points. And what we can do is convert this into a simple distance metric in the form of a dot product. And by now, this dot product looks a lot like attention, where the points in the world are our queries and the pixels in our images are the keys. But there's still one issue that we don't know the full position, 3D position, including the height. So what we can do is simply build this up inside of a transformer as part of a positional embedding. So to go through the full architecture, we'll extract features from each of the views and encode them with this camera-aware positional embedding, where each pixel's positional embedding is given by the intrinsics and extrinsics of each camera. And you can think of these embeddings as vectors that point from the center of the camera to each pixel on the projected plane. After we encode these images, this map embedding, which is learned through training, goes through multiple iterations across attention and builds up a more and more accurate estimate of the geometric layout. And finally, we take a simple decoder and simply upsample this representation to the full map view segmentation. So the full architecture is end-to-end, super simple, and most importantly, fast. With this formulation, we can build map view representations simply by encoding geometry into the positional embedding. So to train these models, we'll need data. The new scenes dataset is a spiritual successor to Kitty and is a collection of 1,000 diverse scenes collected along a variety of different conditions in Boston and Singapore, and I think Las Vegas as well. Each scene lasts about 20 seconds and contains 40 frames for a total of 40,000 samples in the data set. And the recorded data contains a full 360 view around the eco vehicle and is composed of 6 camera views, where each camera view has calibrated intrinsics K and extrinsics for every time step. And more importantly, they also provide accurate hand-labeled HD maps. And with these few things, we have all we need for developing the labels to train this in a supervised fashion. What we'll do is we'll just take the HD map, we'll use the GPS, just crop out the relevant location. We'll take all the 3D bounding boxes and tracks, and then we can put those as the vehicles on this map as well. So on the new scenes benchmark for vehicle map view segmentation, our transformer architecture outperforms several prior methods a year ago and runs much faster compared to similar performing models. On a single GPU, our pipeline actually ran at 40 FPS, which is 5 times faster than Fiery, which is the closest performing model at the time. At this frame rate, model inference is fast enough to surpass the capture frequency of the camera sensors used for driving, and we can actually do some really cool real-time applications. So next, we evaluated different design choices in our pipeline. And what we did was we took the full system and we would just remove various components from the model. And just a reminder, so the keys in our attention layer contain image features as well as the spatial positional embedding. So for these comparisons, the no image features means that the keys only contain the positional embedding. And then no positional embedding means that we only used image features when we're doing the key query attention computation. And the results for the single cross-view layer means that we only used one layer of cross-attention to do the map embedding refinement. And the main takeaway from these experiments is that removing the positional embedding hurt performance the most, which should come as unsurprising, as because if we remove these positional embeddings, we have essentially removed all the spatial relationships across the views, and then the model has a really hard time understanding the spatial reasoning. So there's kind of one little fun fact that the no positional embedding, where we're only essentially using image features as keys, this is like the beta version of our model when we were first starting this project. And this project kind of started out as, wouldn't it be cool if we could just design a transformer to lift the image features into this map embedding. So another kind of ablation that we tried was just kind of randomly dropping out cameras at test time. And so the model here was not trained with this camera dropout at all. This is just kind of like a byproduct of formulating it with the attention. And we can see that, like, as we drop cameras, the IOU kind of degrades linearly, which is nice. There's no kind of catastrophic drop in IOU if we remove one camera. Yeah, and this kind of drop in IOU, it's kind of just proportional just to the area. Like if you dropped out the front right camera, then you wouldn't see that entire region, and there's no way you could really predict what's going on there. Yeah. So here's some qualitative results on the validation sets. So these are like samples we've never seen, and so here we'll see the input views. There's 6 input views to the model, and then here's the model prediction on the right. The gray is road, and then the blue is vehicles, and then here's the kind of ground truth labels on the bottom. Yeah, so this is like the nicest possible scene that we could get. It's nice and sunny. This is just a nice setting. So here's a little bit more challenging setting. It's quite rainy. We can see there's some water droplets collecting on the camera sensors, but the model still does okay. And then here's a nighttime. This is probably one of the more challenging scenes. I think when we were kind of ablating performance across different scenes, nighttime was unexpectedly expectedly one of the more challenging scenes. But here we can see this one actually is not bad. Yeah, so one thing you'll see in some of the models that we were training is that sometimes there's just really large smudges for further away vehicles. And this is, I think, this is just the model trying to optimize for the objective function, right? It tries to just, it will just kind of smear predictions that it's uncertain about. Yeah. So another cool thing that you can do with pretty much any attention model is that you can look at the attention weights and kind of stare at it really hard and see what it's trying to do. And this is one of the experiments that we checked. So we would take a given position in the map view, and then so these would be essentially queries in our cross view attention. And we would look at the computed attention values, which is going to be computed over each of the multi-view images. And what we can do is actually see where in the image the model is looking. And this is just like a nice sanity check that if we're looking front right, we'll actually make sure that the model is looking in that direction. And same thing with this one. We're going to query this top left vehicle, and then we can actually see it's looking at the vehicle on the other side of the road. Yeah, so the one nice thing of the model is that it is kind of built with efficiency in mind. It uses a pretty lightweight, I think, efficient at B2 backbone. And then all of the following layers are just going to be attention and convolution. So it kind of runs very nicely in real time. And then this could possibly be applied to things like online perception, maybe running on board. An autonomous vehicle. And then another cool thing that you can do is that you can take these per frame predictions and then use the localization and then kind of create this kind of global map. And then we can see kind of, oh, this is what happens if you take the per time step estimations and then just fuse them into a global coordinate system. Yeah, so to summarize this work, it's just we introduced a nice way to build these really nice compact map representations, which are really directly tailored towards downstream applications. And this pipeline doesn't require expensive LiDAR sensors and is computationally lightweight, which is crucial for real-time systems like autonomous driving. But to be honest, if you're paying to ride in one of these autonomous vehicles, you'd probably want the vehicle to have every sensor that could possibly be useful. And this is kind of exciting directions for future and ongoing work. So some ongoing research that I think is particularly exciting in the bird's eye view perception is on multimodal fusion. And there's like there's just too many works to put on this one slide for multimodal fusion, but here's some ones I think are particularly exciting. So the top left one is going to be BEV fusion, where they're interested in fusing camera and LiDAR sensors together. And they actually do a bunch of different tasks, not just map segmentation, they also do 3D object detection. And the way that these multimodal fusion methods work is they essentially just put features from all different sensor modalities into this kind of shared representation and then do just vanilla detection or segmentation. But yeah, this is definitely an exciting and really hot venue for like bird's eye view research. Like how can we kind of efficiently transform these features into this representation? And personally, I think the kind of numbers for bird's eye view perception, they're definitely getting there. They're very impressive, you know, after just a couple of years. And I think that the most impactful work for these perception models in the coming years is actually going to be like, how can we get them to run really fast and on board? Another really exciting direction for bird's eye view perception is going to go on how we can design city scale representations of these maps. So all the works that we compared against and what we were interested in was kind of evaluating the performance like per timestamp. But that's not actually what we care about when we're building maps. We would want to compute the performance like as a whole. Like we run one trajectory, let's see how well this map that we built from this one trajectory aligns with like the actual map. And then once we build these maps, how can we actually keep these updated using these fleets of autonomous vehicles? I think these are exciting future directions. Yeah, and with that, that's pretty much it. Thanks for your attention, and then I'm glad to take some questions.
Thanks, Brady. Now let's move to the questions. Anyone from the audience? I guess while the audience are prepared the question, I can start to kick off. So one interesting question that I always have in mind is this argument of different representations, right? So you have shown that one of the main message or the main usefulness of this work is trying to build this efficient map representations that can be used in the online scenario for driving, right? But then this is like the segmentation type map that you're building, and it can be used for city scale or online, whatever format. But there's another emerging trend that's using let's say BV or transformer architecture to build vectorized map elements.
Sure.
So what do you think about these two different representations? Like basically we're going to have some representation for planning. Like which one do you think it's going to be more useful, or pros and cons? How are we going to combine them?
Yeah, so for sure, I think that the so one major thing to consider when you're kind of comparing these different representations is just kind of the resolution, right? And one really nice thing about the vectorized representations is that they can get really fine-grained. They can kind of represent the scene in a really fine-grained manner without that many like parameters, essentially, right? Compared to like if you want a segmentation, like if I recall, each little pixel value in the segmentation was like 0.5 meter or something like that. And we would probably want more than 0.5 meter resolution when we're dealing with driving, right? So I definitely think like but another thing is that I think planners, I think for if you're doing like an end-to-end planner, the segmentation is going to be like a more naturally consumed kind of input representation, at least for end-to-end, right? Because then you can use just some really basic convolution network and then output some points, and like that's your trajectory, and you can call it a day. But I think the vectorized inputs, they're going to require more designs of the planner, like some type of graph-based planner. And then I think the community, at least from what I can see, they haven't really converged on a really good kind of graph planner as of yet. But that might change in like a year or two. So
yeah, exactly. I'm also imagining this kind of vectorized representation for HD map generation is not yet achieving like very satisfying performance compared to this segmentation based method. Although I mean it's going to be probably increase a lot, but
yeah.
So far my understanding that there's still some accuracy issue in order to make it useful, like really useful. But yeah, I appreciate what you just answered. Any other question from the audience?
Yes, I have a question. I would like to ask, how did you do the data alignment for the sensors?
The data alignment. So, yes. So do you mean alignment like spatially or like temporally?
Also temporal alignment from the data coming from the LiDAR and the camera.
Sorry, can you repeat that? It's cutting in a little bit.
Yes, the spatio-temporal alignment for the data from the LiDAR and the camera. You showed that at some point the slide with multimodal fusion. And you had a very nice...
of this thing?
No.
This one.
Oh, this one, yes.
Oh, so this one is like a super naive kind of way of doing it. Like, so for every timestamp, we would essentially get that like local crop of the predictions. All we do is essentially use the GPS location of the ego vehicle as well as its orientation. And you can essentially just like, like push those, like take these predictions and like stick them onto like a global frame.
So it's GPS. Okay, so it's timestamp. Okay.
Yeah.
Yeah. Thank you.
Yeah. So there's a question from the chat, which is how do you handle cameras with different FOVs and distortion in the same rig? Yeah. So this one, it would just be when we're designing this the positional embedding, all we would do is kind of like the intrinsics. You're essentially just describing different intrinsics, and you would just encode that by formulating your intrinsics matrix properly.
And how do you do the data association between the objects from camera and LiDAR? So, okay, you have the objects, you have those, it's not clear how you have them in the bird's eye view, and how do you associate them?
Just to be clear, we don't use LiDAR in the method that we did, like in the crossfit transformers. This one is just kind of camera only, but kind of there's plenty of works that actually do the camera and LiDAR fusion, but we don't in our
okay, I'm not talking about this slide. I'm talking about the slide with the title multi-modal fusion.
And this one or this one?
Let's see, because there's a delay.
And we just to be clear, we don't do any multimodal fusion, just because we're like this method that we presented was it's camera only.
Yeah, it's okay. Yeah, so
maybe one question from my side. You mentioned at the very end that your prognosis is that we already reached a very good level, and you anticipate that now the focus is on deployment and speeding it up on hardware. My question is, how do we know that we reached that point already?
Sure. So okay, so that's yeah, I'm glad you called me out on that, I guess. I guess there's been attempts to see like how good kind of perception is, like is it like in a good enough state. There's that the method, I think it's like the PKL metric, which is essentially a metric of like how good your perception outputs are, which is more directly tailored towards downstream planning. But in terms of like how, like, is it good enough? Yeah, I think there's no way to know if it's good enough. Like they'll just keep kind of pushing the numbers. But I do think that the kind of perception numbers for these tasks are getting like very competitive with like they are like the detection, just looking at the like detection MAP and things like that, they're getting like very good. And then I think the the work that you can do to get a lot of impact is going to be on kind of getting it to deploy, because most of the methods that work at the state of art are not fast enough.
Right. Yeah.
There's one other question in the chat.
Oh yeah. So the question is, are there any insights on how to improve the robustness under sensor failure and weather conditions? So I would, for sensor failure, you could always essentially do some data augmentation. I'm not sure how much it helped, but yeah, you could probably do data augmentation, just dropping off cameras, like faking some type of sensor failure noise. And then weather conditions, I would say that one would have to be just collect more data.
Thanks, Brady, for answering all the questions. Oh, there's one more. Yeah. Is there any difference between dropping the front and side cameras?
So I'm not sure. When we were running that experiment, we were just kind of like dropping them at random, but that's probably something we should look at.
Yeah, I imagine maybe there's a different impact on downstream planning, but since my understanding, you're only evaluating the perception, right?
Mm-hmm.
Yeah. Okay. Thanks, Brady, for answering all of these questions. And thanks the speaker again. And now move on to our next speaker. Hi, Lingdong.
Hello, I'm here.
Yeah, you can hear me. Yeah, I can see your slides as well. All sounds good.
Great.
Yeah, yeah. So let me introduce Lingdong, and then we can get started. Yeah. So Lingdong, our next speaker, is a PhD student from National University of Singapore. His research interests include 3D perception, domain adaptation, and visual representation learning. He pursues to build robust and scalable perception systems that can be generated across different domains and scenarios. And today, Lingdong will give the talk around robust perception in autonomous driving. And now the stage is yours. Feel free to take it.
Thanks, Xinggang, for the introduction, and hello, everyone. My name is Lingdong, and today I'm going to introduce some of my personal insights about building robust perception models for autonomous driving. So first, a short introduction of myself. I'm a PhD student in the School of Computing, Department of Computer Science at the National University of Singapore. And my research interests are 3D perception, data efficient learning, and robustness. And for 3D perception, I'm particularly interested in LiDAR segmentation, 3D object detection, and monocular depth estimation. And also there are applications under the semi-supervised learning, unsupervised domain adaptation, and representation learning settings. And I also have several industry experience. I was an autonomous vehicle intern at Motional, working with the semantic mapping team. And we are also developing the MM detection 3D code base. So this code base is now no longer for just 3D object detection, but also we are supporting the LiDAR segmentation related tasks. For example, LiDAR semantic segmentation and panoptic segmentation. So we just released several benchmarks for those tasks. So if you are interested, so feel free to visit this repository. So today's topics are, we have two topics for robust perception. And the first topic is the robustness under data efficient setting. Because the autonomous driving data is very expensive to from the annotation perspective. So we want to train the models with not all the fully supervised learning settings, but also we want to train the models under semi-supervised supervisions. So our goal is to achieve satisfactory perception performance with limited annotations. And the second topic is about robustness under common corruptions. Like the first speakers talked about a little bit about the sensor failure and different weather conditions. We are also interested in that. We are aim to test the perception models with different corruption scenarios, and our goal is to achieve reliable perception performance under those out of distribution cases. So first topic is the robustness under data efficient setting. And for this topic, we are going to introduce laser mix. This is a framework for semi-supervised LiDAR semantic segmentation, and it was accepted to CVPR 2023 as a highlight paper. Laser mix is a data efficient learning framework designed for LiDAR segmentation. It leverages the spatial prior in driving scenes for data efficient learning. It constructs low variational areas by a laser beam mixing, and it encourages the model to make confident and consistent predictions before and after mixing, and it can achieve competitive results over the full supervision counterparts with, for example, 2 times to 5 times fewer annotations. This is a brief introduction, brief summary of this work. And this framework, with this framework, we can achieve satisfactory results under a limited annotation budget. For this example, we use only 1% annotations from the semantic data set to train the model, and also we leverage the remaining 99% unlabeled data to help the train the model, so it can be robust across different scenarios with only a limited budget. So first, a little bit introduction about autonomous driving perception. Here we are talking about different kinds of tasks that are formed by the LiDAR point cloud. For example, the LiDAR semantic segmentation and the panoptic segmentation, and also the 3D object detection, and the tasks that combining all of them is the LiDAR 4D LiDAR panoptic segmentation. And here we are interested in the LiDAR sensor because it can provide us with the accurate depth sensing ability, and it's robust under the different lighting conditions. And also, the most importantly, it provides us with the dense perceptions. So this is a little bit about the background. And here we are talking about LiDAR semantic segmentation. This is one of the important tasks for 3D scene understanding. It aims to assign a semantic label for each point in the LiDAR point cloud, as shown in this demo video. So one problem with this task is that the annotation of the LiDAR point cloud is very expensive. Let's just take the popular semantic KT dataset as an example. Annotate a single frame LiDAR scan in this dataset costs up to 4.5 hours. So which is pretty expensive, especially much expensive than annotating an RGB image. There is a recent work resorts to the weak annotations to save the budget. For example, this is the Scalable KT dataset. The LiDAR scan are annotated using light scribbles, which reduce the time cost to only 10 to 25 minutes each. But however, the huge amount of LiDAR scans still constrains the annotation process. So in this work, different from previous pursuit, we target on the less explored semi-supervised LiDAR semantic segmentation. And our goal is to leverage the abundant raw LiDAR scans for training accurate segmentation models. So we propose laser mix to make the advantages of the spatial prior in LiDAR scenes for effective learning with semi-supervisions. So this is our observation and motivation. Unlike the general 2D or 3D segmentation tasks, the spatial cues or spatial priors are especially significant in LiDAR data, where the certain class tends to appear at the certain areas around the ego vehicle, as shown in the heat map here, and also the class distribution along the range distance. So because LiDAR point cloud serve as this perfect reflection of real-world distributions, which is highly dependent on the spatial areas in the LiDAR centered 3D coordinates. For example, the top laser beams is traveling outwards long distance and to perceive mostly the vegetation, man-made, etc. While the middle and bottom beams, laser beams tends to detect car and road from a median and close distance. So we propose laser mix to mix those laser beams from different LiDAR scans. And then we encourage the segmentation model to make consistent and confident predictions before and after mixing, which can be general across different LiDAR representations, because this process is happened during at the data level, so it's not sensitive to any kinds of representations, for example, the range view and the voxel view. As a result, our overall pipeline significantly outperform previous SOTA methods in both the low data and high data regime. So it can also serve as a strong data augmentation for training the data under the fully supervised learning setting. So the laser mix operation follows a three-step procedure. The first step is to partition the captured LiDAR scan into low variational area based on our observations on the spatial prior. And the second step is to efficiently mix every area in the LiDAR scan with foreign data. And the third step is to encourage the LiDAR segmentation model to make confident and consistent predictions on the same area in different mixing. So here the mixing happens along the inclination and azimuth direction which can be calculated based on the point coordinates as shown in this equation. So it's a very basic equations for calculating the different feature embeddings from the point cloud. And this figure shows this illustrative example of partitioning points into different areas. So the laser partition, which we believe can effectively excise a strong spatial prior in the LiDAR point cloud, because based on our assumption, we want to mix the current area with every area from other scans. This is computationally expensive. So because the cost for directly computing those marginal probability is very expensive, so we want to mix the scan in this way. It can help to efficiently reduce the training overhead. And this figure shows our overall pipeline. We have two branches, the student net and the teacher net. And during the training, a training batch is composed of half of the label data, as shown in the blue, and also the half of the unlabeled data, as shown in yellow here. So there is a balance between two kinds of data. So we will need to subsample the upsample the label data so that they'll have a relatively equal number of training scans. So we have after the label scan is first fed into the student net for the predictions and calculate the predictions and the loss from the supervisions. This is the Euro, the conventional way of training a LiDAR segmentation model. And as for the unlabeled scan, we first fed them into the teacher nets to generate the prediction, and we set a threshold for filtering the low confident predictions, and we keep the remaining ones as the pseudo labels for the unlabeled scan. So these are the two different pipelines for different kinds of data. After this, we mix the labeled and unlabeled data together by our laser mix operation along the azimuth and inclination direction. And then for the mixed data, and also we also mix the ground truth for the label data and the pseudo labels for the unlabeled data. So they are mixed in the same way as the input data. And then we fed this mixed data into the student net. It can calculate the mixing loss, and then we backpropagate the loss through the student net. So here the teacher net does not have any gradient updates. We follow the conventional way of using the EMA exponential moving average from the student net to update the weights of the teacher net. So this is the overall pipeline of our framework. And we have some detailed derivations for theoretically prove the effectiveness of this framework, but due to the time limits, I will just skip these slides. So if you are interested in this, you can check our paper for more details. So here comes to the experimental parts. We test this framework on 3 different data sets. There are the NewSync, Semantic Kitty, and the Scalable Kitty. So they are very different database. The NewSync is a low-res LiDAR database because it uses the 32 beam LiDAR sensors to capture the LiDAR point clouds. And differently, Semantic Kitty and the Scalable Kitty has the high-resolution point clouds captured by the 64 beam LiDAR sensor. And also the Scalable Kitty has the weak supervision, which corresponds to only around 8% of the supervision signals compared to the Semantic Kitty. And also we want to compare between different modalities. As mentioned before, there are multiple different representations for LiDAR segmentation. For example, the most popular ones are range view and voxel. There are also other modalities like the bird's eye view and the multi-view fusion, like the fusion between different modalities. So in this work, we adopt the range view and the voxel because the voxel is currently the best performing representation, and the range view is the like the most efficient way for in-vehicle LiDAR perception. As for the data split, we choose randomly 1, 10, 20, and 50% of the scans from the original data sets as labeled data, and we assume the remaining ones are unlabeled. So this is our settings. We only use the supervision signals from those labels, from this label split, and we want to leverage the remaining ones as the unlabeled ones. So this is our comparative study with the previous works for semi-supervised learning. So firstly, the sub only here is the supervised only settings, which means that we only train the models using the specific number of labeled scan. So this is kind of the lower bound of this task. And we can see that across different database data sets, there are if we involving more supervision signals, and the performance will become better. So this is very intuitive, and our goal is to restore the performance under the semi-supervised learning setting. We want to leverage the remaining unlabeled data for training a more powerful segmentation model, which can achieve better scores on a validation set of the data set. Because this spatial prior is also appeared from the image domain. For example, this is from the cityscape dataset. So we also test this framework we also compare the laser mix with the previous work on semi-supervised image segmentation. So we can say that this spatial prior is also helpful for improve the performance for image model. And here comes to the ablation study. We mainly do this kind of ablations for the previous consistency considering the empty loss and also our mixing loss. So we can see that the mixing loss is actually contributed to most of the improvements for this framework, and also try to use either the student net for generate the pseudo label, or using the teacher net for generating the pseudo label. So we can say that the teacher net can have like more stable predictions than the student net in this case. So in our final framework, we choose to use the teacher net as the generators for generating the pseudo labels. Another comparison is among different mixing techniques, because this laser mix operations share some similarities with the previous 2D mixing techniques like the cut mix, cut out, and mix up. So we also compare this effect to further attest that the spatial prior is actually playing a very important role in this framework. So we can say that the performance of laser mix is much better than the previous work, like the cut mix. The cut mix also have the spatial prior because the same semantic class point tends to be clustered, and it tends to reduce the entropy in any continuous area. So it can also improve the performance over the baseline. But the mix-up on average cannot improve the performance because there is no distinct patterns in random points. So this is our observation. And also we have the ablation study for other hyperparameters in our framework. And furthermore, we study the best possible mixing strategies in laser mix. Because we can have two directions for designing different mixing techniques. The first one is along the inclination direction, like we have different rings centered around the ego vehicle, And the second direction is along the azimuth. We can see, for example, if we split it into two areas based on azimuth, then we will have a front view and a back view. And if we split them into more areas, we will have more views around the ego vehicle. And we can also combine the different directions together to form more complex mixing. So our conclusion here is that if we mix along the inclination direction, like shown in the horizontal axis, then the performance can be greatly improved over. But if we just mix the scans along the azimuth direction, which means that we want to mix different views from different scans, because this operations is not actually enforcing too much spatial prior, because the front view of the and the back view of the LiDAR scans have like very similar patterns. But if we mix the scans along the inclination directions, and the different patterns along this direction from different scans can be mixed together, so we can better leverage the spatial prior in this driving scenario. So this is our public resources of this work. If you are interested in this work, you can check our paper, and also we have the code on the GitHub. So feel free to give us a star if you are interested in this. Okay, the second topic we are going to talk about is the robustness under common corruptions. So for this topic, we introduce this work, benchmarking 3D perception.
Hi, Lingdong. Sorry for the interruption. Just in the interest of time, how many slides you have for the second topic?
I just have like 6 or 7 slides for this.
Okay, sounds good.
So
let's go for
approximately
it.
2 minutes.
Okay, sounds good. Yeah. Sorry for the interruption.
I will make this quick. Okay, so the second work we are talking about the perception robustness under common corruptions and sensor failure. So because we are working on a very because autonomous vehicles are operating under the real world case, which is complex, and so for the image domain, we already have some work creating such a benchmark for testing the robustness of the classification models. And also for the indoor point cloud, we also have this benchmark for the classification and the part segmentation of the object-centric point clouds. So in this work, we introduced the robust 3D benchmark for evaluating the robustness of LiDAR-based 3D perception models. By perception, we mean the semantic segmentation and the 3D object detection tasks. So we benchmarked 34 of them, and we analyzed some design recipe of how can we improve the robustness of those 3D perception models. Here are the taxonomy of our benchmark. We have 8 different categories from weather and lightning conditions, motion and sensor failures, and data processing issues. So these are some examples of those different kinds of corruptions that we simulated. And we also test the models from different representations, as mentioned before. Some statistics of our benchmark are in this slide. And we design some metrics for comparing the robustness among different models, like the mean corruption error and the mean resilience rate. These are the 2 indicators for in our benchmark. So our result shows that there is a strong linear relationship between the corruption error and the clean accuracy. So which means that if we can achieve better accuracy, then the model tends to have a better robustness. But the trend is getting more and more flat. So it's important for us to consider not only the clean results on the benchmark on the leaderboards, but also the robustness under those kind of OD cases. And we have several key observations, but due to the time limits, I will just, if you are interested in these observations, you can feel free to check our paper and our benchmark. So that's all for my presentation. Thank you.
Thanks, Lingdong, for the wonderful presentation. So now I think we are about right on time, so we can have 1 or 2 questions. Anyone from the audience? Okay, so I can go first. I have one question regarding your first work, the semi-supervised learning for LiDAR segmentation. So, I mean, right now there are a bunch of work. Even in today's presentation, there are other speakers talking about using CLIP or using foundation models to scale up the performance or scale up the model with unsupervised data, right? Or using features learned from like larger scale unsupervised data. So I'm just thinking, what's your view or what's your thoughts on this kind of semi-supervised work in this area of unsupervised learning or foundational models, right? Because imagine if we can do this with some text prompt to do LiDAR segmentation without any supervision, what's the usefulness? What's the use case of this semi-supervised learning approach? Or are you imagining there are some ways that we can combine these two types of methods to further improve the performance, or like what are the pros and cons or different use cases of these two different settings?
Okay, thank you for asking. It's a very good question, and it also points out the future directions of this task. From my personal understanding, because currently the foundation models are mainly from the 2D domain, which means that we have multiple vision foundation models trained on a larger set of image collections. But for the LiDAR point clouds, this is a different thing because those point cloud datasets are not that huge enough for training generalizable models across different LiDAR datasets. This is one thing, and the second thing is that because different LiDAR segmentation datasets tends to have different configurations, like the different FOVs, different number of laser beams. So this kind of discrepancy causes some problems in training unified models. So these are I believe those are the constraints for to have a foundation model for LiDAR segmentation. But actually we can see that there are some future promising directions of leverage the vision foundation models for 3D segmentation. For example, recently the CLIP and the segment anything models, because some of the 3D datasets have the correspondence between 2D and 3D, like the previous speakers introduced. For the new things dataset, we have the multi-view cameras, so we can leverage such data for using the foundation models. We can perform the segmentations on the image domain and then project the segmented masks onto the 3D point clouds by using the LiDAR camera correspondence. Then those forms previous segmentations, 3D segmentations on the LiDAR point clouds. Then because this process is completely unsupervised, we do not need any ground truth labels for either 2D and 3D. So by having this, we can have a bridge between the 2D like we can leverage those projected masks for designing some pre-task tasks. For example, we can do contrastive learning on the 3D point clouds by using the augmentations on the projected super points, and then we can pre-train the segmentation model, LiDAR segmentation models using those kind of information. So it will, I mean, I believe it will ultimately give us the chance to like combine because we can still have some certain number of annotations to form those few shot learning settings, which is very similar to semi-supervised learning. So we first pre-train the segmentation models in this way using the projected superpixels from the image. Then we use a very limited budget for future fine-tuning. Then we can more or less to achieve the similar things as the image foundation models do. We can have like more generalized abilities across different LiDAR data sets. Yeah, so this is my personal opinion.
Yeah, thanks a lot for the thorough answering here. Any other quick questions from the audience? Okay, so if there are no other questions, oh, sorry.
No questions.
Okay, sounds good. Yeah, if there are no other questions, let's move forward. And thanks again for the speaker, Lingdong.
Yeah, thanks for having me.
Yeah, take care. Okay, so now we are having our final speaker, Xinggang. Hi, Xinggang, can you hear me? Yeah, I think I can see your slides. I can see your slides. Yeah, and
Okay.
I can hear you as well. Okay, so let me introduce you first, and then feel free to take it from there. So our final speaker is Xinggang Wang. Xinggang is a professor at Huazhong University of Science and Technology, and he was visiting scholar at Temple University and also UCLA. His research topics include large-scale and efficient visual representation learning for video understanding and also autonomous driving. And today, Xinggang will talk about large-scale transformer for various tasks in autonomous driving. Looking forward to your talk, and feel free to take it from here.
Thank you, Xinso. I'm very happy to give a presentation about our recent work on transformer and autonomous driving. So transformer has been very popular in computer vision and autonomous driving. So in this talk, we will talk about transformer for 2D and 3D representation learning, and transformer for map construction and vehicle motion prediction. So we have worked on BV representation for a few years, and so this is a very typical setting in autonomous driving, and we have multi-view images. So in this case, we have two problems. We have think about two problems. The first problem is 2D representation learning. So we have many multi-view images. Currently, we usually use residual networks and swing transformers for 2D feature extraction. Do you think these are final solutions? And the second question is about the BV representation learning. So how to obtain the BV maps and from the multi-view features and perform detection, segmentation, and map construction. So transformers has been very powerful in computer vision and NLP and other fields. So this is we know BERT and GPT are very powerful using the self-supervised learning and a large amount of data. So in computer vision, so there's a trend to there are many works want to achieve the BERT moment of computer vision. So there are two works I list here. The first one is the BERT pre-training of image transformers. So this is from Microsoft Research Agent. So this work is pretty strong, and the main idea is to map the image patches into tokens using a tokenizer, and then once the patches are tokenized, we can just do the same thing as BERT. So the mask image, the masked patches will be removed will be replaced with using the mask token, and the visible visible tokens will be inputted into the transformer, and the transformer will be decode the value of the tokens of the mask patches. So this is bait. So we need a tokenizer. In bait, the tokenizer is VAE. And the second work is by Kai-Ming He, and which is very, this is a very famous work, and the name is masked autoencoder, in short MAE. So different from bait, MAE perform feature reconstruction or feature decoding in the pixel space, and the input image. So this makes the framework very clean and very slim, and it do not need any encoder tokenizer. Sorry. So and both bait and MAE think they should both can perform self-supervised learning without labeling any pixels, and think this kind of method can be scalable. And in this PR, we had a method, a paper termed as EVA. The full name is exploring the limits of masked visual representation learning at scale, and this is a highlighted paper. So actually, in this paper, we do not have a new method, and we just replace the encoder tokenizer from the VAE to clip. So I think I just learned listened that Xingshou also mentioned that the using foundation models to help to learn from unsupervised learning, unlabeled data. So this is also similar to Xingshou's idea. So we have a tokenizer clip, and this can also be we can think about this is a teacher. So teacher or tokenizer is actually the same. So in the top stream, there's no mask patch, and the teacher takes the unmasked patch, and then we can do mask image modeling and to perform feature reconstruction, and so we can perform self-supervised learning in this way. And we just scale up the pre-training process. So we have for example, we have a basic size of clip, and we can use it to learn or to supervise a 1 billion parameter vanilla transformer, and train it using the publicly accessible data. And once the EVA transformer is trained, and it can be used for many downstream tasks, and actually we have get state-of-the-art results on a broad range of representative vision downstream tasks. Here are some details. The EVA transformer has 40 layers, and it's a vanilla transformer, and it has 1 billion parameters. It is trained using 30 million publicly accessible images, and the training cost about 128 GPUs for 14.5 days, and it is highly optimized and it trained using the 30,000 image for 150 epochs, and you can see that the images are from typical computer vision data sets. For example, ImageNet 21K CC 12 M and 63 meaning objects 365 Coco and 80 20 images. And you can see these are results for image classification, video classification, Coco detection, segmentation, and Coco stuff semantic segmentation, and AD20K semantic segmentation. And this shows some typical foundation models, for example, Florence and big swing transformer, again swing transformer V2. And here are the previous best results released in the papers, and these are our results. You can see on these tasks we are all better than the best methods, and typically you can see this is the zero-shot performance, and average zero performance among all zero-shot ImageNet classification task and the kinetics video classification task zero-shot. And so these results are pretty impressive. So later we will see more results and why it is so good. And this shows the results for ImageNet 1K classification. So actually we can get results higher than 90%, and in our new versions. And this is so this had not before there no paper has been had results than better than 90% only using public data. So, and here shows the robustness of our method. So we have this kind of experiments, and you can see this is the standard results on ImageNet 1K, and this results on ImageNet V2 and ImageNet Real, and ImageNet with adversary examples, and ImageNet with sketch images. So you can, once we test on this kind of complex ImageNet datasets, and we can observe a performance gap between the original ImageNet results and the complex ImageNet results. And previously, for example, BAIT and MAE, and this kind of method has more than 10% performance drop, but our EVA only have 5.6 performance drop. So this is very impressive. And here shows some detection and segmentation results on Coco. And you can see EVA is the state-of-the-art method, and it is better than swing transformer, and then Dino detector and mask Dino, and BAIT with BAIT 3, and group data V2, and other good methods. And there's a very impressive result, at least in these slides. You can see, so this is the performance on Coco dataset. We can see the previous best performance on Coco dataset is 63, and we have about one point performance gain. And this is significant, but it's not so significant. But in LVS object detection, and you can see the previous best method is 53, and our method, our results is 62. We can get about 9% improvement. This is very significant, and this kind of result can also be seen in instance segmentation. So we all know Coco and LVS are contain the same image, but have different annotations. In Coco, we only have 80 classes, but in LVS we have about 1,000 classes. So LVS, so the results show that the EVA method can representation have already conquered the non-vocabulary instance segmentation and object detection problem. Actually, we also can use EVA to initialize a clip model, and using once we have good clip model, we can have once we have a better clip model, and we can perform machine learning modeling training to get a better EVA model. And if I have a better EVA model, we can get a better clip model. So this kind of bootstrap training, and this is very useful. And so why EVA helps clip, I highlight here, and it can stabilize the clip training process and accelerate convergence and improve the performance. And the MM training is also very useful, because in clip we only have global representation learning, and in MM training, and we can introducing local representation learning, and we can use unlabeled images, and so we can use lots of complex unlabeled images. So this is why the EVA model is very good. And here's some EVA clip results. So it is also better than OpenClip and OpenAI clip, and much better, significantly better. And the EVA project is open source, and currently we think that this is the largest and best and most complete open source vision foundation model that supports lots of downstream tasks, and it is also the first 1 billion parameter open source open source model with leading performance. Yeah, and all training data are open source, and so this I think this code base is also the first SOTA code base. And here shows some results, and I think so this is our university, and we use the EVA instance segmentation model trained on Coca and test the video in our university, and shows good results. Also, I will take this opportunity and to welcome everyone to visit our university, and which is Huazhong University of Science and Technology in Wuhan. And if you visit Wuhan, and you can drop me an email, and I will take you to visit our university and enjoy the food in Wuhan. Okay, so the EVA model also has been applied in Salesforce Blip 2, and in the open source project Mini GPT-4, and in MIT Foundation offset Hansong in Hansong's lab, Song Han's lab, and they worked on offset tuning of foundation model, and they also use the EVA model as a typical case. And then I will go. I will talk something about 3D repetition learning, and because this workshop is about 3D deep learning for autonomous driving, and so because EVA is for 2D, and hopefully it can be used for 3D. Okay, and for 3D, and I think BV is a very good solution, and actually, so previously, I think Brad Zhou. Actually, I really like Brad Zhou's work. Yeah, I like the CVT method. So to get the BV representation, there are different methods. For example, we have two kinds of methods. For example, the second kind of method is actually it is CVT, cross view transformer, and it's purely it is a pure transformer method. And the first one is a pure geometric-based method, it requires precise depth as prediction and camera parameters. So actually, so we had a work which is placed on our CAF and it terminates geometric guided kernel transformer for BV representation learning, and our idea is to use the camera parameters to roughly get the prior 2D positions in multi-view and multi-scale vision maps. For example, and we for this point in BV, we can roughly estimate its position in multi-view images. For example, we think so after calculation, and we know this is this point is correspond to, so it only contains in this area. So when we using the queries to calculate the BV representation, and we can only query this part, and we do not need to calculate compute the attention outside this part. So this is a very simple idea, and it can make the whole BV map learning process faster, and even more, we use a lookup table to index for indexing to get rid of camera's parameters at runtime, and we have some results, so it can be slightly better than CVT, and actually we have some ablative studies to show that our method is our method is robust to camera parameter derivation. And the second work, the third work is about map reconstruction. I will be very fast. Okay. So map is very, very important in autonomous driving. So we have different kinds of map, and previously we use a lot of resources to construct offline maps, but it is cost a lot of things. So we know, and for online map reconstruction, online map reconstruction is a very interesting topic, and it is low cost, is highly automated, and no maintenance and scalability issues. But it has limitations. Previously, the map quality is very low, and the method, the speed is very, very, very low. And we have one paper is termed as actually it's a map transformer, so we termed it as MAPTER, and the MAPTER is published in Aclio this year. So we can see this results pretty good, and so we have a map transformer, and the input are 2D multi-view 2D images, and we use the for example, we use our GKT, geometric guided kernel transformer, to get the BV representations, and we have a map decoder. To have a map decoder, there are two core problems. The first one is how to divide a map into instances, because similar to data detection transformer or other transformer-based method, even in CVT, we have a concept of instance. If we have the instance, we can use a query to represent an instance, and we can perform hierarchical Hungarian matching. And once we have the instance, we can perform Hungarian matching to get the map perception results. So, but in this case, our instances are kind of more complicated. We use polyline and polygon to respectively to represent open shape map element and closed shape element. Similar in this kind of way. So the lines and the polygons will be divided into fixed point or fixed number of points. And when matching, we have a hierarchical matching strategy. First, we'll perform point-to-point matching using the Manhattan distance. And once we have the instance level matching results, and we can perform Hungarian matching to perform set-to-set matching. And here are the results. So we can show the results are very, very impressive compared to previous online map method, for example, vector MapNet and HD MapNet. Our results are very, very fast, and it can be real time on a very common GPU, and it can be also very, very accurate. And you can see the MAP is much better than the previous methods. And we also show the map modeling results, and we show that our permutation invariant map modeling method is good, and we can also compare with other BV representation learning method, for example, GKT, LS, and IPM, and GKT shows good results. And here are some visualization of MapTor in different cases, including sunny and cloudy, rainy and light. So MapTor can be very, very robust. So the last one is about motion prediction, and we also have one paper on archive. Is for end-to-end motion prediction. So the basic idea are very simple, and we can use the instance the BV. We can it is based on BV representation, and we can use in the detection segmentation results get the actually, it's also based on queries. So we can have queries for map and for cars, and we also have a query for the self agent, and it can be interact with all the map elements and the other cars, and then perform the motion prediction in end-to-end manner. So this is the final slide. So it is my outlook about deep learning for autonomous driving. So our idea is to embrace a large scale pre-training for autonomous driving. So I really think we should have a EVA style pre-training visual representation in autonomous driving for 2D image representation, and once we have 2D representation, we can get the B representation. I think actually we have some standard solutions, and I think most people know the standard solutions. So in this part, we can include other modality information, for example, And once we have the B representation, and we can perform, we can use all kind of queries. We have detection queries, segmentation queries, map element queries, motion queries, and then we can perform planning. In the planning part, I think the GPT style pre-training is also very important. We can perform self-supervised autoregressive learning, and we can have a planning GPT and finally solve the problem. And the whole part, the solution can be optimized end-to-end manner, and finally solve the problem. And thank you very much. And this is all.
Thanks, Xinggang. Thank you so much for your presentation. I would have to say I'm a big fan of your paper and presentation. I really love a lot of the paper you presented, and even including the one that you looks like you didn't have the chance to present, the VAD paper, vectorizing representation for AV, like the very recent one. But again,
I think due to the SV policy, I cannot talk about the paper.
Yeah. But yeah, I mean, it's on archive, so everyone should be able to see it. I really like that paper as well. But also kind of recalls me a lot of memory for the university, for the campus, Huazhong Keji Daxue. I've been there because I was a student of Wuhan University and just traveling to Guanggu, you know, a lot of times. Yeah. Okay. Anyway, so I guess we probably don't have a lot of time here, but we do have some. Maybe we still want to have some questions. Anyone from the audience, go first. Otherwise, I do have a lot. Maybe I can have one to get started. So actually, this one question is really similar to the one that I asked Brady earlier. Like it looks like what's your work, and this final slide, I really like this one. You're a really big fan of this transformer-based representation, like this EVA style representation throughout the whole AV stack, right? And then, I mean, I feel like this is one of the promising direction, but on the other hand, there are a lot of working on this occupancy or BEV representation, like BEV former or occupancy-based representation, like Tesla, what Tesla is doing, right? So they are not really, I mean, some part of their network, they're trying to infer or reason this vectorized representation, such as for online mapping, but there's still a large body of their full network is learning this BEV full representation for planning. I can imagine that there are different use cases. For example, if we are doing this vectorized mapping here, like your work, MapTR or VAD, I'm not sure like how well it will perform, for example, in very complicated scenarios such as intersection, and also maybe with a lot of occlusion. I'm imagining if we're doing this BEV type of representation, I mean, the other kind of group of who are working on this, they could argue that this BEV representation can naturally encode the uncertainty, such as maybe there are some lanes and connectivity between lanes. If the network is unsure, the BEV representation may be kind of blurry there. But if we are doing it in a vectorized way to output this vectorized representation or these polylines, whenever there's a misconnection or a wrong connectivity between different lanes, would that mislead the downstream planning network, right? So I just want to get like a high-level thoughts. What you are thinking about this? Not sure if I make myself clear.
So thanks for the question. I think this is a very good question. So planning is very actually planning is very important, and it's because it's about safety, and also planning is also very hard. So previously planning is based on so rule-based planning is also very important. So I think in this slide, actually we can add more element in this pipeline. For example, if we have, I think as an occupancy is also can. So maybe we can add the occupancy representation in this part. Actually, I think occupancy is pretty similar to B representation because we just need to add another dimension into kind of above BV. So we can have occupancy here and this kind of 3D B representation. So maybe the name should be changed. So I think for planning, all kind of information can be input into the planning part, and because besides the perception results and the information of the ego vehicle is also very important, and we should have simulator to, for example, to get a lot of data. Maybe not simulator. We can collect the information of the ego vehicle, and so from in the real cases, and to train the planning GPT. So this is our basic idea. Maybe cannot be fully answer your question. Thank you.
Yeah,
Thank you.
Yeah, I think that's pretty good. I'm just trying to imagine like how we're going to how the field is going to move, right? You imagine this kind of motion transformer, you're still outputting some kind of trajectory, because this is what I read from the VAD paper that's you recently have, and also the map transformer, you're outputting all these kind of different polygons, these lane segments, right? But on the other hand, if we output occupancy, it's going to be like pixel based or voxel based.
Yeah. So
and then-
maybe I think there's a possibility to get a sparse representation for occupancy. Yeah. So occupancy is dense. Maybe there's a clever way to use query to learn occupancy. Maybe I also think this is very, very possible. Yeah.
Yeah, definitely. Yeah. Okay, sounds good. I don't want to occupy any longer time. Are there any other questions from the audience? Yeah, I guess if no other questions, maybe I can have one more. So regarding this EVA, I'm also I know, I mean, the performance of EVA is awesome. I mean, it's kind of very popular right now. I just want to get a sense of what do you have some like secret sauce there? I mean, training this kind of really large scale transformer model, because I mean, this is not really ideal. Like ideal wise, it's pretty simple, right? But you really make the one that's achieving like super strong performance ever. So I just want to know what are the some of the like top 1 or 2 challenges that you have encountered and solved when you're developing these kind of large scale models.
Okay, so I think so I just learned from my student Yuxin, because he's the student working on this project. So I just talk about this. So Yuxin has lots of experiments on optimizing transformers. So I think there are two ways of talking about this. So maybe optimization is all you need, and or loss of GPU is all you need. So Yuxin has lots of GPU in BAI, and currently he's working in a startup, and he also has lots of GPU. Because when training large scale transformers, so we should make this whole system fast. And if it is fast, and we can find heuristic to make it better. And I think there are many training tricks, and so all tricks can be found in our open source code. So yeah. So this are the secrets. Yeah.
I see. Okay, so iteration speed is critical, and also optimization, and also compute resources, I guess.
Yeah.
Okay, sounds good. Yeah. If there are no other questions, final call, and then we can end here. And thanks again for our fellow speaker, Xinggang, and thanks a lot for presenting. And I hope I can have a chance to meet with you at Wuhan sometime in the future.
Yeah, in the future. Welcome to welcome back. Yeah.
Okay. Yeah. Take care. Thank you so much.
Thank you.
Yeah. Okay. So now I think we have all our speakers presented. Maybe let me screen share to give the closing. Oops. Okay. So again, thanks everyone for attending this workshop. So we got quite a lot of attendees. I guess some are online and some are at the actual workshop. And thank you everyone for listening and participating, and also giving the insightful questions to engage with speakers. And yeah, I think that went all very good. And also, we would like to also thank our speakers. For sure, we have a really excellent list of speakers that having very diverse expertise, as Rev introduced in the opening. And we hope to see everyone in the future in person again at other workshops or conferences. And finally, I would like to also thank the organizer team, especially Ravi, who really spent a lot of time putting this all together, contacting the speakers, scheduling, and working with the conference organizer for the workshop and everything. Yeah, and also thanks a lot for Agabias for being there on site to make make this really happen. And without them, this workshop is not going to really possible. Yeah, and again, thanks everyone for the effort. And yeah, finally, a lot of other questions, a lot of other people have asked about recordings, and it will be shared online, I think. We will also post on LinkedIn and other social media, so feel free to look at it afterwards. Yeah. Yeah, I think that's it. And thanks everyone for attending again. And yeah, have a good night. And then we hope to see everyone again in the next year of the workshop editions. Yeah, thanks.
Thank you.